Hey everyone, I'm Krishu Bhavsar, and I'll be talking about a project I've been working on that involves implementing deep Q learning in the game of Snake. So first of all, what is Q learning? So in a sentence, Q learning is a model reinforcement learning algorithm that uses deep neural networks to obtain an optimal action given a particular state. So first of all, what does reinforcement learning mean? So reinforcement learning is just a process that involves teaching a software how to behave in an environment by telling it how good it is doing. So for example, let's say you want to teach a dog how to do a new trick. Well, you can do this by giving it a treat every time it does a trick correctly. And so you can do this in a similar way with software. You can reward the software every time it does something good, and you can penalize the software every time it does something bad. And that's basically what reinforcement learning is. And Q learning is a specific algorithm. It's a piece of reinforcement learning, and that's what we're going to be implementing in the game of Snake. Alright, so let's get into how I organized this code, right? So I had three different classes: the agent class, the game class, and the model class. And in our game, it worked by having a game loop that runs all the time. And during each iteration of the game loop, I had a playStep function which takes in an action. I'll get into what an action really means later on, but for now, just know it takes in some type of action, and it returns a reward, a game score, and a game over, whether or not the game is over, and also the game score, right? Alright, and then we have this agent class over here, which sort of puts everything together. So it has to store an instance of the game, and it also stores an instance of the model. And then we have this training part here, which is basically what we had to implement. It's basically the heart of this AI. First thing it does is it gets the state from the game. What I mean by state is that it gets the current situation that the snake is in. And then based on that state, it calculates a move. So we have a get move, and the get move function returns an action. So what does the snake have to do? It's the snake's action. And this is found using a function in our model called model predict. Okay? Then we can play a step in our game based on the action. So we play that move, we make that move, and based on that move, we get the reward if the game is over or not, and we also get the snake's game. Now, based on that new information, we calculate a new state, and then we have to remember that old state and the new state in our model, and then we train that model based on all that information, and then we keep repeating that process over and over again until our agent gets better and better. Then we have the model class. It has these functions: the predict function, the train function. A model right now is just going to be a linear QNet, which is used for just normal reinforcement learning. It's pretty simple. It's just going to be one input layer, one output layer, and then one hidden layer. And I'll get into exactly how the structure of the model is going to look, but for now, we just know that we have a model predict, which takes in a state, and then it returns an action. Alright, so now let's get into the reward system. So this is how we're rewarding our snake depending on its actions. So let's say it eats the food. We want to reward it because that's something that's good. You want the snake to eat the food. So we're going to give it plus 10 points, for example. And then if it collides into something, we're going to take away 10 points because that's not something we want it to do. Because if it collides into like a wall or itself, or even into an obstacle, the game is going to be over, and that's bad for the AI. And then if it does nothing, we don't want to reward it or penalize it. So for example, if it's just moving around the map, it's not doing anything necessarily bad, it's not doing anything necessarily good either. So we just don't give it any points for that. Alright, so now let's get into the structure of the action and state, right? So we have a snake that has to perform some type of action. So what does this action look like? So for now, to keep things simple, what I've done is that I give the snake three options, right? It can either go straight, keep going in the direction it's going, means going straight. It can turn right, and it can turn left, right? And this can be denoted by in this notation over here, which it can just be an array of values that vary between 1 and 0. So if the 1 is in the beginning, it means it's going straight. If it's in the middle, it means it's a right turn. And if it's all the way at the end, that means it's a left turn. So this is sort of what the snake can do. Then we have the structure of the state. So this is a little bit more complicated because we need to give the snake decent information so that I can work off of that information to calculate an action. So right now what we have is we denote all of these values are denoted by a 0 and 1, and if the danger is straight ahead, then we have a 1. If the danger is on the right side of the snake, then we give that a 1. If it's on the left, then we give that a 1. We also tell the snake which direction it's going, if it's left, right, or if it's going up, or if it's going down. This is relative to the map. And if the food is on its left, if it's on its right, if it's above it, or if it's below it. So that's the structure of what the action and state looks like. Alright, so now let's get into what the structure of the model looks like. So as I said before, we're going to have one input layer, so that's this layer over here, and one output layer, and we're also going to have one hidden layer. Right? So the input, right, is this state, or this current situation that the snake is in. So that, as I said before, we had 11 different parameters. So we denote that by giving it 11 different input nodes in the input layer. And then we also have the result, which is the action. And there's 3 different outcomes that can come from here. So we're going to have to denote that by giving it 3 different output nodes in the output layer. Right? Then we have the hidden layer, which is just, I gave it an arbitrary value of 256, which just worked out. I'm not going to get into exactly how hidden layers work, but I do have a research paper that's written, and you can read more about hidden layers and what they do in that paper. So now let's dive into the code. Alright, so I have my code open over here. It's just a very simple snake game. Over here I'm just initializing the game. Over here I'm placing the objects, which could be food or obstacles, since I have 2 different modes. One is with obstacle mode and one is without any obstacles. So depending on if I have obstacle mode on or off, I'm rendering the obstacles here. I have a playset function, which I talked about before, and I have a function to check if there's a collision in the blocking with the snake. I have an update UI function, which basically just updates the UI of the game. I have a move function, which moves the snake in the direction that the snake is going, and I also have just a main function here that runs the game. So if I just open up a new terminal over here, and real quick, I just type in Python manual.py. Should run the game here, and as you can see, this snake game works. Right now there is no AI, it's just me playing the game with my keyboard, and you can see the score counter goes up. Pretty simple. When I collide into myself, just need to get a little longer. So when I collide into myself, the game ends. If I hit the wall like that, the game also ends. It's a pretty simple game, nothing too complicated about it. Alright, and then I made some changes to the game itself. So before we were checking if there were keyboard inputs for the manual version, but now since we have an AI, we are just going to check the action that's returned from our model over here. So that's going to be the new direction. So that's what we're doing. There's some other changes, but I'm not going to get into that. It's not that important. So let's get into our agent class, how that's implemented. So we have this agent class over here. Over here we're initializing some parameters. This one is just a counter to see how many games are played by the agent. The epsilon value, which is something I'm going to mess with later on, is an exploration rate, which basically means it's a rate at which the agent chooses a random value over a predicted value by our neural network. And that's important because sometimes you want to bring some variability into it. So if there's no randomness in our in our model, it's not going to learn anything. So there has to be some introduction of randomness in the beginning, and then over time we use more and more of the values that our model predicts instead of using random values. And then we have this gamma, which is a discount rate. I'm not really going to get into that right now. If you want to read more about it, you can look up what a discount rate does. Then we have the memory. Again, this stuff is not really that important. We have the QNet over here, which is the actual neural network that I initialized. This is just a class I have in the model PY, which basically I initialize it to 11 inputs, 256 nodes in the hidden layer, and then 3 outputs. And then we have just a trainer, and then I'm not going to get into this either. It's just a different class I have in here, which is used to train our neural network. Then I have the get state. This basically just returns the state that the snake is in. So you take in a game, which is the game itself. It just checks if there's a danger ahead, if the direction what direction the snake is going in, if there's food ahead, and etc. And it returns an array, which I described earlier. And I have remember, which basically just appends the new states into the memory. And I also have a get action function, which basically just returns a move that the snake has to perform. And we have our train function here, which trains our this is a whole loop that I described earlier, includes all of these other functions inside. So this is where I'm calling all of them. I initialize the agent, I initialize the game, and then I have a loop over here which I perform. And I call all these methods here, and at the end I'm also going to graph, just the current score and the mean score that the snake has. This is something interesting to see for results. Again, I'm going to go into the model class over here. I mentioned this a little bit earlier. This is just me initializing the neural network. It's just a simple feed-forward neural network with one hidden layer. Alright, so let's just run this real quick to see how this works. So I'm going to open up a new terminal and run our agent class over here, which is just, just going to initialize the game agent and start the game. It's going to take a second to load, but once it does load, right away we have our snake moving around. It's at a really high speed right now for training sake, because the games are it's going to run for almost like 200 games, which is a lot. So it's boring to watch also, so I sped it up by a lot. And you can also see that I have the obstacle mode on for this version. So occasionally you will see some triangles that pop up, the red triangles, those are obstacles. So if the snake collides into those triangles, then the snake dies. Also, I have a graph over here which represents the score of the snake. This is the blue line is current score during that game, and the green line is the mean score, so the average score throughout all those games. I'm also logging that information in the terminal down here. So you can see, the game number it's on, which is also shown over here, net game number 30, the exploration rate, which you can tell it's going down every game it plays, because what you want the agent to do is you want the agent to rely less and less on random values as time progresses, and you want it to rely more and more on the neural network itself. So over here you can see it's just learning how to play the game. You can see that the mean score is gradually increasing, and that's because it's getting better and better at playing the game. So it's learning that eating food is good, hitting the walls is bad, hitting any triangles is bad as well. So I'm just going to fast forward a bit so that you can see how good this snake really gets. Alright, so as you can see, the exploration rate over here, it hit 0, And that's because I had my N number set to 50, and what my N number is just the number of games the snake plays with a randomness variant in it. So after 50 games, for example, the snake relies completely on the neural network and there's no randomness. Now every action or every move it makes, it's coming straight from the neural network. It was just spinning around, it's been spinning around in circles, but when it realizes that it's more profitable to eat food rather than spin around in circles, that's when the score is really going to improve. You can see already that it's avoiding all the obstacles and eating all the food. There's some hiccups along the way, because you can see it goes straight up. It goes to around like 14, it looks like, and then it jumps straight down to 0. It's still learning. There's no like definite like recipe that it has in order to score the best, but yeah, I'm just gonna let this fast forward a bit more so you can see just how much it improves. Alright, so now you can see we're about 100 games into the training, and you can see it goes straight for the food most of the time. It will learn to avoid the obstacles, which is good. It's not that consistent, as you can see from the graph. There's a lot of ups and downs, but you can see the overall trend is really improving over here. You can see that it went from almost getting nothing to a record of 44 points, which is incredible to see. Alright, so something interesting I did was I messed with the maximum random games number, which is basically a number to denote how many games we're playing with the random variant in it. So this also determines our exploration rate. So our exploration rate is going to be calculated based on this value. In other words, it's our epsilon value, just another name for it. And you can see over here that we're subtracting the maximum number of games from the number of games it runs. So, for example, if I have this to set to 50 and I'm going to be testing for 200 games, for 50 of the games, it's going to play with that exploration rate. The rate is going to, even though the rate is going down over time, it's going to start off at 25% and then it's going to go down from there. Because you have 50 games out of the 200, so that's 25%, and then as it plays more and more games, it's going to go down from 25% eventually until it reaches 0, and it's going to reach 0 at the 50th game it plays. So from the 50th game onwards, the snake is going to play the game with just the neural network and no randomness in it. And so I messed with this value. I changed it from 50 to 100 and 150, and I gathered results just to see how it impacted the learning. And my results are actually pretty interesting. So if I open up my results over here, you can see that with an initial exploration rate of 0.25, which is just like 25%, I had the snake learn pretty well. So you can see that I have a mean value of around like 17, and I also have a record of around, this looks like 47. It did pretty well. It just was pretty volatile. But again, it still learned decently well. Now, if I change the initial exploration rate to 50%, you can see over here that compared to before, it took a little bit longer to learn or get a hold of how the snake game is played. And you can see that because it takes this distance from here to here, it takes around like 110 games, it looks like, to really get good at it, and it has a much steeper jump from like a lower number to a higher number. So compared to here, it's more of a gradual increase going up, and over here you can see it gets steeper. Now if I increase the initial exploration to even more, you can see that this really gets really steep. So you can see it takes way longer. It takes almost 150, 160 games for it to get good, but you can see that it shoots up from almost nothing to above, well over 50. So this looks like what, 52, 53? A record of 53, which is significantly better than our initial exploration rate with 0.25. But it did take longer to train, and it's also way more volatile. You can see it goes from 53 back down to 0, and that's just something I found interesting. And you can see over here that the mean value is way less than our simulation with the initial acceleration rate set to 0.25. So yes, it did take longer, but the record score is way higher, and it is more volatile. Alright, so that's all I wanted to talk about in this video. Thanks for watching. I'll link my GitHub with the source code in this down in the description, and I'll also link my research paper. Again, thank you for watching. I hope you enjoyed.